everyone. Thank you for coming. Really excited. So my name is Guy Kaplan, and I'm an NLP researcher at WSC Sports. So today we will talk about retrieval systems and how we can use agentic workflows in them. I will show you how you can keep your retrieval systems flexible so you can adapt to new data without training your models. And we will see how we can increase velocity by cutting down development time. We'll also see how we can stay efficient and avoid complex maintenance. So let's have a look at a live example. This is an article taken from the NBA website. Okay, it's written by a sports commentator. It's about a recent game between the Knicks and the Hawks. Okay, we know that today, most people don't actually read, that's not the way they consume their content. They don't go ahead and read articles. They would prefer some video to summarize it for them so they can relax and watch it. So that's exactly what we do. Our goal is to create a short video based on this article. So our system takes this raw article, analyzes it, understands which players are being mentioned, which teams are being mentioned, is there a specific play involved, maybe it's about a game, about the entire season, and creates informative sentences that represent this article. We then take these sentences and we match a video clip for every one of them. Now let's see how this looks like live. Okay, so when a sentence references a person, we will see him on the screen. It could also mention a team or a specific play. In that case, that's what we would want to see on the screen. Okay, so you can see how all the videos are from the same game. It doesn't really have to be that way. Okay, so we're in the business of telling the best story in a concise and engaging way. What we're talking about is automated storytelling at scale. Okay, this is how our system turns articles into videos. First, we have our input, the raw article like we just saw. Then our system summarizes it and generates these sentences. This is all fed into our retrieval engine, where the entities are extracted and used to find the video clips matching the sentences. And as a post-processing step, we put it all together, we create a nice video like we just saw. We overlay the sentences. So today we're going to focus on the retrieval engine, okay? And we'll show you how, using agentic workflows, we can be prepared for any kind of input with relatively little effort. Okay, let's see what types of challenges me and my team are up against. First, we have our search space, over 800 million segmented clips from different sports, different leagues. We need to deliver results in up to minutes from a request, and we're optimizing the precision at one metric. You see, in most search engines, it's okay if we have good candidates in the top 5 results, but in our case, we need to be right on the very first shot, because we're actually generating a video. And as far as impact goes, we have very high broadcast standards. Okay, we serve clients like the NBA, ESPN. Millions of people watch these videos daily. So when we make a mistake, that's for everyone to see. So let's start with an exampling of tackling this problem. Okay, this is a sentence that our retrieval engine can get. Okay, Johnson shattered the long-standing mark for most assists in elimination road games during yesterday's thriller. Now, if you're an NBA fan, you might think this is about Jalen Johnson. He's a rising star playing for the Hawks. But if you're not a fan, you might just see Johnson. And unfortunately, this is exactly where technology also gets confused. So many of us might already be thinking how we can solve this, right? Like, what's the big deal? We have semantic similarity. That's how it's usually done these days. So let's try and do that, and we'll see the problems. So how is it usually done? We get the input, okay? We take our sentence, we treat it as some kind of query, we apply some transformations, we encode the text along with any context we have, and we get a representation vector. Okay, this vector is used to find the nearest neighbors in a vector database, where we find up to k candidates. Similarity is usually defined by cosine similarity in this case. So let's see, this is like the embedding space. Let's see what the technology does with that. So the target query falls somewhere in this space, and the red cluster is where the model thinks the answer is. Okay? The encoder looks at the text, looks at the tokens, and it sees Johnson, it sees record, it sees assists. And what he's trying to answer is who is most statistically probable match for these tokens in the history of basketball text. So we got a few candidates, Magic Johnson. For the non-fans, Magic Johnson, he's a famous NBA player. He broke many records. He's also famous for his assists. And in the history of the internet, the text Johnson and record and assists, it's just much more likely to be mentioning Magic. So to a vector database, this is a perfect match, okay? But to our use case, where we want to show Jalen Johnson breaking the record, that's really, really bad. Johnson is like 30 years old, played like 30 years ago, okay? He's like 80 years old. He's really old man by now, so that's a really bad output. We don't want to see him referencing yesterday's game. So why does this actually happen? Embeddings, they optimize for semantic probability, not factual truth. There's a few missing pieces here that we'll talk about them shortly, but we have an implicit entity here, Johnson, and we also have temporal blindness. The model just ignores yesterday, treats it as noise. Now look at the actual clip we need. Jalen Johnson, the one that broke the record, way off in the corner, low similarity. Using this method, the system can't hope to find this video clip. So we'll get video clips like this.
Pistons have got to steal. They're not going to get a chance. Green will win it.
Now that's a nice assist, but showing it about yesterday's game, that's a really bad thing to do. Okay, so let's ask ourselves questions that an embedder can't answer. First of all, who is Johnson? There's dozens of Johnsons in the NBA league. There's Magic, Joe, Jalen. Also, when was yesterday? Yesterday is relative to the article date, not the server time. And what is an elimination road game? That's a logical state of the world. Okay, that's not just a few keywords. And of course, whose record was broken? So the text implies there is someone who held this record beforehand, but it doesn't really mention him. So if I gave this query to a human video editor and asked him to actually find a good clip, they wouldn't just type Johnson and hope for a good result, right? They would actually stop and think. They would check the date, look at the article defined yesterday. They would check the schedule, who played yesterday. They would cross-reference. They would look, is Johnson playing for any one of the teams? Then they would verify. They would see if it was actually an elimination road game. And at last, they would find the game, go over all the assists until they find the one that broke the record. That is what they will select. So this is just a series of logical steps, okay? Grounding, verification, and refinement. And this brings us to our solution. We call it agentic retrieval. Our system needs to be able to identify missing information, to gather context with tools, to resolve ambiguity, to execute precise searches, select or re-rank if we're talking about retrieval lingo, and of course, the ability to backtrack in case nothing fits. Okay, so today, I'm going to walk you through the architecture that we built in order to automate this workflow. We moved from blind execution to having a system that thinks before it searches. And while I work in sports, this methodology is universal. Okay, it could be about last week's medical symptoms, or in financial data, maybe relevant to some new trend. This agentic framework solves the problem of retrieval with incomplete information while staying flexible. Okay, so let's start by looking at a standard retrieval pipeline. So we start with an input, like the sentence we saw. Usually there's a step of input understanding, some information extraction, entities extraction, maybe transforming the query a little bit. Then we have the search policy. So every use case requires a different searching strategy. Then we look up in the database. It could be a vector database, it could be a relational database, doesn't matter. It gives us candidates. We then re-rank the candidates using some algorithm until we get the top K results as an output. So today I will show you how we changed these three stages and into agentic workflows, trying to imitate human reasoning. The first two stages, they can help us optimize the recall metric, having better candidates. The re-rank stage can help us achieve higher precision, maybe making better ranking or selecting better. Okay? So we will start with input understanding, go on to search policy, and finish with re-rank. So let's dive into input understanding. Let's revisit the semantic similarity approach. We saw that when we take an input, we embed it, and then we search, we get the wrong results. We saw how the embeddings landed on Magic Johnson instead of Jalen Johnson. So this is because embeddings optimize for semantic probability and not factual truth. So the main takeaway here is that in many cases, raw input lacks context. Okay, we need to extract the implicit information and enrich the query with explicit knowledge in order to overcome this problem. So the new flow should look something like this. We have our input, we understand it, we try to ground them into actual terms, agreed upon terms, or even IDs in the database. Okay? So regardless of the domain, the pattern is the same. We take vague human language and transform it into precise, searchable terms. So one popular way to ground these entities is using a knowledge graph. Those are extra popular today. There's automatic ways to do them. So what is that? It's a structured representation of information or entities and their relationships. So instead of relying on vague semantic similarity, we explicitly define relationships inside the data. So it would look something like this. We would have all our players, we know which players played for which teams, and we know which teams played against which other teams, and we know when these games occurred. So in runtime, we would take our input, we would traverse it through the graph. Whenever we hit a node, we take it, extract it, and use it as an entity. So that's one way to do it. But there is a few problems. Let's see what the drawback of a knowledge graph is. So generally speaking, a graph is a snapshot of when it was indexed. Okay? There's no understanding, semantic understanding about yesterday's match or this morning's trade. Another issue is that we have predefined relationships. We define the relationships before we actually make the graph. It doesn't matter if it's manual or automatic, the relationships are static, okay? So niche records and unusual achievements, they have no place in the graph. And at last, maintaining a knowledge graph can be expensive. We need to research it, we need to optimize the graph. It can require a lot of effort, and also adding new data to the graph is not always straightforward. Sometimes there's no other way, and we have to re-index the entire knowledge graph. So let's dive a little deeper into the predefined relationships, and I'll show you why that's not just an issue that we're dealing with, it's something that any product can face. So every product makes assumptions about its input data, right? There's no free lunch. We make assumptions based on the business needs. So when we first started with this product, we looked at our customers' articles, and we tried to understand what kind of articles we should be expecting. So we designed our system that way. We saw that many of the articles discuss player statistics, some discuss team statistics, and so on. But in reality, our original design covers only a fraction of what our customers use our system for. So we have new intent types that emerged after launch. Our customers saw that we have this system and started using it on different articles that we weren't expecting. So that is just data drift, and that's inevitable, okay? But in some domains, it's especially severe. And in our specific product, it's inherently part of the product. We're trying to be always general to any type of article, okay? The reason why it's so severe in our case is because we have a variety of different customers. They all have different domains, they use different language, and their data also changes as the year progresses. Okay, so because our input is so flexible, a knowledge graph is not the right fit for us, okay? The relationships in the knowledge graph are static. So this leads us to extract entities in a more naive way, okay, and handle the harder cases in a different manner. So what did we do? First, we understood the different entity types. They require different amount of effort, okay? So there's easier cases where we have a closed set, a small closed set of entities, like actions. We know about all the actions in the NBA. We know about the assists, the dunks, the floaters, everything. Okay, so we can just simply extract the action and then match it using rule-based methods. Then we have a harder set of entities, stuff like players and teams. Those have a bigger pool of candidates to choose from, and they might be also implicit. Okay, so for these, what works for us is extracting with an LLM with as much context as possible, and then matching it to IDs in the database, using also an LLM. And then we have the harder cases, the ones that we use the heavy tools for. We call them temporal entities, things that have a point in time, like games, like a specific game moment. Those are harder cases, and we need to reason over the input along with the relative time and whatever other context we can gather. Okay, so let's look at an example of that together. So look at this input. James became the first player in NBA history to score 40,000 points. That's a real sentence. Now, how can we find the game that is being referred to here? It doesn't mention any game. Okay? I'll tell you one thing, a knowledge graph won't work here. No relationship can connect this specific sentence to a specific game. And why is that? Because the relationship literally didn't exist before it happened, right? Now, this begs the question, how would a human handle this? They would probably search with Google. Okay? Every sports outlet covered this. So instead of trying to anticipate every relationship we will have in our input data, we gave our agent a search tool. Okay? It will use it selectively and understand when the game occurred. So we're actually still using a knowledge graph here, but we're just not maintaining it. We're using an existing one, which is also indexed in real time, and it's also very good, like we know. So this is the main takeaway from this part, okay? External search can be used like dynamic knowledge graph that someone else maintains. That's a lot of heavy lifting that we're moving to someone else. And let's see how our game matching algorithm works, okay? We have our input, like we saw, James became the first. We feed it into our game matcher agent, which reasons over the input. Understand, is there a game being mentioned here? If so, it uses the external search tool. Using the search tool, it understands when the game occurred. It has some dates. And then using these dates, it can connect to our database and retrieve games that happen in these dates and then reason over them and select the most probable game. So we have our input, the sentence, and the output of this game agent is game ID. Okay, so we made all of the entities in the input explicit. Now let's talk about the search policy. Okay, so now that we have all the entities, we have Jalen Johnson, we matched it to an ID in the database, we have the game, and we also have the correct action. Now, what do we do with all the information that we gathered? Okay? If we have a vector database, we can simply aggregate the context and filter by the date using the grounded entities. We'll have a vector representing the input. And if we have a relational database, we do something similar. We're just constraining the search space using the grounded information. Okay? But remember that we also have another hidden entity here. Okay, we have whose record was broken. Okay, let's say that LeBron James held the record beforehand, and our smart system found that entity. Okay, but to our specific use case, this entity is completely redundant. Okay, remember we're looking for a clip that broke the record, and LeBron James is not in it. So using this entity in our input, it will introduce noise. Now, in the best case, we'll just have no candidates using it. In the worst case, we'll have noisy candidates. Maybe a clip of LeBron James playing against Johnson or something like that. So the question is, how can we decide which entities we're going to use in our retrieval? So a good starting point can be using some linguistic heuristic, okay? Maybe like identifying the subject. So in this case, it's Johnson, and we can say, okay, because Johnson is a subject, let's use that entity. That can cover many cases. But what happens if we change the sentence, but we still have the same intent? We're looking for the same clip. So we change the sentence, and now James is a subject, but we're looking for the same clip. So we can see this is not really practical for different input types. So how can we solve this? Let's take a step back again and think about how a human editor would approach this. It would ask, what am I actually looking for? And then they would answer, Johnson's assist in Game 6 that broke the record. So using that understanding, the editor would simply select the correct entities. They would ignore LeBron James. So that's what we try to do as well. Okay? So the main takeaway here that a human editor does not search for, with every entity that they encounter. They understand what they need to do based on the use case. So that's something that we must want as well for our system. We need to, first of all, realize that noise is inevitable. Okay? We can have redundant entities. We can make errors along the way. And also that use case is what drives the selection. So this is how we do it. We have our input along with all of the context we gathered. We input it into the intent agent, which formalizes an intent. Bring me Johnson's assist that broke the record. This is fed into our query builder agent. Based on the intent, it creates a query, a set of queries, set of searches, and aggregates all the results into a candidate pool. Okay? Now, what happens if the searches yielded no results? Or maybe the intent wasn't good enough or wasn't constraining enough? The query builder could just backtrack, just like a human would do. He would find anything, he would just change, okay, I'm not going to look for that clip, I'm going to look for something else. So we answered the flexibility problem by reasoning on the use case, and we also relaxed the effect of noisy information by allowing the agent to backtrack. Okay, so next up is re-rank. We have our candidates. We gather them from the query builder agent. Now what? So let's look at some common approaches. We have BM25, that's a classic. It's been around for decades. We have bioencoders, where we pre-compute the candidates, and then in runtime we only compute the query and get a score. Then we have cross-encoders, which take into account both candidate and query, and we have a new emerging one, LLM as a judge, okay? We use a language model to reason over which result is better. So we can ask something like, given this query, who is the most likely candidate? Okay, there's many solutions for this. There's open source as well. It's very popular today. We could also mix them by ensembling. We can hand out weights to different scoring methods. And we can also cascade, filter along the way. We start with a large pool, we filter until we end up with a smaller pool that an LLM can rank in the end. But there is one strong assumption that we're making here, these scoring methods at least, they're making here. And the assumption is that the answer is already in the pool, okay? But what if it's not? And how can we even tell? So let's take a step back and think how a human editor would solve this as well. They don't make these assumptions. Us humans, we don't do that, okay? They do two things differently. First, when a human sees candidates that they are unsure of, they don't just guess. They apply more effort. They investigate. And they also have the ability to backtrack, okay? If nothing fits, the editor can just step back and say, okay, I'll try a different search, or I'll try a different intent. So how do we give our system these two abilities? We need two things. We need investigation tools that we can use on demand, and we need the ability to backtrack. So let's start by looking at what investigation tools we have in our case, okay? For example, we can use video analysis, computer vision, just like a human would actually open the video. We also have commentator transcripts. We can use speech-to-text algorithms and extract the text, and we can have a fairly good signal. If the commentator said he broke the record, that could maybe point us to the right direction. Okay, but we can't, those are very, very good signals, but we can't run them on all of the candidates or even all of the database. That's not practical. Okay? These need to be used selectively, only on the top candidates or candidates that we are unsure of. Now, this is not just unique to sports, right? In medicine, we have imaging scans. In finance, there is fraud detection models. Those can be expensive as well. So expensive signals, they exist everywhere. You just need to use them selectively. So let's take a step back and see how we solve this problem with the re-ranker agent, okay? We have our candidate pool. We use some cascading methods to narrow down the pool as much as we can. Then we have a re-ranker agent that has these different tools, using investigation tools. Then the re-ranker agent decides, are there any candidates that fit the intent, or do I need to backtrack? And how does it all look together? Okay, so we have our input, we start with that. Then we have our input understanding phase, where we apply some information extraction. In our case, that's entities that we're actually extracting from the text. We ground them to actual terms. We then take that into the search policy, where we have an intent agent that formalizes some intent, then passes it on to query builder agent, which creates searches, aggregates the candidates, and then they are left for the re-ranker agent, which selects the top K results and gives an output. Of course, the agents have the ability to backtrack if something goes wrong along the way. So, let's summarize what we've seen so far. First, we have input understanding. We saw how important it is to ground information to agreed terms. And we can also use external tools. In this way, we can outsource the problem and have zero maintenance. Second, we have the search policy. By understanding the intent based on the use case, we can use the information we extracted selectively and remain also drift-proof. And third, we have re-ranking. We can apply extra effort on suspected candidates using tools on demand, right? We also can backtrack just like a human would do. So the bottom line is, let the system reason like a person. You will ship faster with less overhead. Thank you for coming to my session. It's been really great. Feel free to approach me after this session. Also in LinkedIn, you have the QR code. And enjoy the rest of the conference. Thank you.